Minerals are the building blocks of the earth. But did you know that minerals themselves are commonly made of shared building blocks? We can use the analogy of Lego blocks in the sense that Lego blocks have different widths. So, for example, they have a width of 1, 2, and 3 highlighted here. And they can also be linked in different ways, such as these Lego Technic bricks, to make buildings and different structures like spaceships, for example, and anything that you wanted to build in your childhood. You've probably heard of the mineral groups biotite, pyroxene, and amphibole, and these are collectively known as the biopyrobles. And they're modular minerals that are built on beam-like building blocks. The biopyrobles are important because they're abundant and diverse on the Earth. They account for about a quarter of the Earth's crust, which means that they're found in most rocks, and they're diverse, so they actually account for about a quarter of the silicate species known to science. And because they're diverse, we can actually use their subtle differences in chemistry and also structure to understand the geological history of a rock from formation to the present day. We can make a comparison to another mineral group such as the feldspars, and we can see that although the feldspars are a little bit more diverse or a little bit more abundant than the biopyrobles, they're much less diverse than the biopyrobles, which means that they're not actually as useful geologically for understanding geological processes. Now, the problem with the biopyrobles is that because they're so diverse, they're also very complicated. And so, for example, here's a bunch of different mineral groups and different names, and it makes it very difficult to understand the structures of these minerals and let us use them to understand geological processes. And this is also one of the reasons why a lot of students and a lot of geologists hate mineralogy class, because it's really difficult to understand these minerals, and they're very important, right? Currently, we have a few different ways that we can look at crystal structures of minerals. There are ball and stick models. So in this case, we've got these wooden balls that are colored, and they're attached to these metal spokes or sticks. And the good thing about these ball and stick models are that they're physical, so they're 3D, so we can actually move them around and see what their structures are. But there are a few problems with these models in the sense that they're expensive, so they can cost upwards of $400 per model. They're very complicated because they've got a lot of different components, and they're very static, so you can't take apart a module and build it back together because there's too many components, right? There's also visualization software, so this is on computers, and this is in a virtual environment, so it's rendered on a computer screen. They're great because they're free. We can change the complexity of these structures by just changing the visibility of certain features, but they're dynamic, and that's only really for one structure, so we can't actually compare other structures, at least very easily. So an ideal teaching aid that would help us look at these structures would be physical, so it would be 3D so that we can actually move it around. It would be accessible so that it'd be quite low cost, so it's affordable for everyone to use. It's simple, so we don't need a lot of understanding of the structure to understand, the relationships between these minerals. And it's dynamic, so we can actually use the same structure for many different structures. And taking all this together, we sort of formed a question of, can we use modular mineralogy and 3D printing to actually communicate mineral structures in a way that enhances the current visual teaching aids that we use for crystal structures? So first of all, we've got to try to simplify crystal structures. So there's a few different ways that we can represent a crystal structure. The most simple is by representing all these atoms as these balls. So this is a space filling model. And then we can improve on this by joining different atoms with these sticks representing bonds, but this is still quite complicated, and so we can simplify this even further by joining the oxygen atoms into this polyhedra, and now we can start to see the structures and the fundamental backbone of these minerals. We can simplify it even further by taking out some of the sites that maybe are not so important, and now we arrive at this representation. And so what I've done is I've actually 3D printed this in a modified format, and now we can really, really see the building blocks, the fundamental building blocks that make up this structure. And remember that we're looking at modules that are essentially these beams, and we're actually going to look at only the cross-section of these beams, so they extend in and out of the page. So what we can see here is that there's two main modules within these modules. There are the tetrahedral blocks, where silicon and aluminum will fit. And there's also these blue or green octahedral blocks where iron, magnesium, and sometimes aluminum will fit. And we'll sandwich another tetrahedral block so that we get these TOT modules. And this is a really important theme within the biopyramidals. So now let's put this all together. We've got a building block of 1 unit width, and what we can do is we can actually connect another building block of 1 unit width to make a building block of 2 width, 3 widths, and also we can continue that to infinity. We can also connect the blocks so that they have a vertical offset, and there's 2 ways to do this. So in this example here, we've got this top T module, which is connecting to the O module. And in this situation here, we've got this top T module that connects to the bottom T module of the second module. And so if we repeat this pattern for the other module widths, what we find is that these combinations reflect the different mineral groups within the biopyramidal family. And so this is one of the ways that we can use modular mineralogy to actually break down the relationships between different minerals and really understand what's going on with the crystal structures of these minerals. Now we can go further and we can actually look at how the crystal structures of these minerals affect the physical properties of these minerals. For example, habit, so how minerals will grow. And in this case, periodic bond chain theory is a theory that suggests that crystals will grow in the direction of the strong bonds. So for example, the mica group, the linkages between these modules are quite strong, so they will extend left and right and also in and out of the page, sort of in a plane. But they're quite weak when it comes to the vertical direction, as you can see here. And so what we expect with the mica group is that it will actually grow into these sheets. It's a similar idea for the amphiboles, except that for the amphiboles, they're actually in these double chains. And again, the linkages between the modules are a little bit weaker. And so what happens is that the amphiboles will actually grow along the lengths of these modules into prisms and also needle-like or acicular growths. And it's an even more extreme case for the palygorskite group because they really have these sharp or very, very strained and weird linkages between these top T modules and bottom T modules, and that leads to an acicular or even massive habit. We can look at cleavage angles. So the pyroxenes and the amphiboles are commonly found in many rocks. And because they're quite similar in terms of their colors, we need to use their cleavage to distinguish them in the field. So for example, pyroxenes have a 90-90 cleavage, whereas amphiboles will have more of a 120-60 cleavage. And we can actually use our understanding of crystal structures to break down this, or to understand the differences in these cleavages. And specifically, the idea is that, again, the linkages within the modules are very strong, whereas the bonds linking the modules together or linking different modules together are much weaker. And so we can see that, for example, in the structure of pyroxene, that they would break along these linkages. And that's where we get this 90-90 cleavage. It's a similar idea for the amphiboles, but with the amphiboles, they're a little bit wider. They've got a module width of 2, and so that actually squishes this angle to a 120-60 angle. And we could actually continue this idea into infinity, and the infinite case would be represented by a mica group mineral, which is essentially a sheet or an infinite width chain. And we can see with the micas that they have 1 cleavage, and we could consider that as actually 2 cleavages at 180 degrees and 0 degrees. We can also look at how crystal structures affect color. So for example, in the mica group, the biotites, they're often colored by iron, and because the iron is found in these octahedral modules, if the light is running parallel to these modules, as you can see here, if it's polarized parallel to the sheets, that will actually cause much stronger coloration. So in conclusion, when we apply 3D printing and modular mineralogy to communicating crystal structures, we find that they're both accessible and interactive. Accessible in the sense that the blocks will be open source, so anyone can print them. They're low cost, and they're also multi-use, so we can use them in different ways. They're also interactive because they're physical models, and we can actually physically move them and see what happens. So we can, for example, physically break apart a structure and see what those cleavages would be. And so in total, we've got a lot of applications in geoscience outreach, education, and also research. For example, we could use TotBlocks in interactive exhibits in museums and science centers to really show visitors, how minerals are related to each other, and they're as simple as building blocks, as simple as Lego blocks. We can also use them in displays and also remote teaching. So, for example, with the COVID-19 pandemic, we could actually do remote teaching in labs. So in the future, what we're hoping to do is we're hoping to continue working on these blocks. So we actually very recently, just on Monday, we had our first successful integration of TotBlocks in an optical mineralogy lab. So we talked about the relationships between different minerals, and also their relationships to macroscopic properties such as habit, cleavage angles, and pleochroism. We're working on a peer-reviewed publication, which hopefully we'll submit around May of 2022. And this will be in Geoscience Communication. We're also going to include a bunch of assembly videos, so videos describing the different groups of minerals and how to construct their structures. And this paper will be an open review, and so that means that anyone can actually comment and leave feedback. So if you're interested in that, definitely keep connected with me and stay connected to this project. We are currently working with some science centers and museums to actually put this in a space where the general audiences can actually interact with these different models. And the hope is to design more mineral structures. So, for example, I've made the structure of quartz in a similar way. But really the sky is the limit in terms of what we can do with 3D printing and mineral structures. So if there's nothing else that I can leave you with or that you can take away from this, let it be that success is built on mountains of failure. And so I've made a lot of mistakes along the way. I've also had a lot of successes. And with every failure, there's always something new to learn. And to me, that's probably the most rewarding part of what I've done with TotBlocks so far. And if you'd like to follow this project or follow me and follow some of my research, you can do so through the following links.